Hi guys, I'm gonna go over the homeworks from the connectivity. And the first one, what you wanna calculate us to calculate is the vertex connectivity, the edge connectivity. So let me get it a bit lower here. The edge connectivity and the minimum degree of the vertices. And we know the reason that they ask us to do these three is because we actually have these inequalities. So perhaps let's start with the degrees. That is helpful, right? Because this will cut down the values of these two connectivities. Uh, Perhaps, I don't know whether I have stressed this last time, but if you think about it, if one of these values is 0, remember this actually means that the graph is disconnected, right? If you do not need to remove anything to get a disconnected graph, well, that was because it was disconnected. Okay, now, of course, all these are connected graphs, so that's not going to happen. So for us, since we are dealing with connected graphs, this will be 0. Okay, so let's calculate the degrees. I'll put this here. That is 2, 2, 1, 2, 3, 4, 2, and 2. So we see already that this number, in this case, is 2 here. And that means, okay, these values are either 1 or 2, right? So now we have to see. Is there, let's start with the edge connectivity, the vertex connectivity, the smaller of the two. Is there a way to, is there a vertex that if I cut it out, the whole thing becomes disconnected? And you see immediately the central vertex is somehow taking too much traffic, too much task upon himself, right? If you think of it as a network, see, if I remove it, I get two disconnected components. And so, yes, so this means, so we have here B, sorry, I'm in black now. So B is a cut vertex. So this tells me that the vertex, so the vertex connectivity of this graph is 1. Because if I remove this B, the one guy, then I get disconnected. What about an edge? Well, it seems no matter which edge you remove, you can always go around, right? So let's, if we try to remove this edge, we still everything is still connected. If I remove this edge, and it's rather symmetric actually, so that's of course. So the only two types, right, is the ones that connect with the central guy or these types, but neither one disconnects the whole thing. So this means, so there is no edge, a cut edge. What this means that lambda, the edge connectivity must be at least 2, because otherwise it would be 1. But it is at most 2, so we know that lambda of g is 2. So that's how you can figure this out. And why is it at most 2? Well, because of degrees, right? If we take one of these degree 2 vertices and remove all the edges that connect to it, well, of course, we get it's isolated. Okay, that's for the first one. So let's do this for the next one. Also, again, let's do the degrees. 1, 2, 3, 1, 2, 3, 1, 2, 3. Here's quite a lot. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. Okay, so these are the various degrees. So here we see, let me, I'm gonna do this. Okay, let me do this way. Can I must have a dotted line here. Let me get some dotted lines. So, okay, I hope that is, I try to put everything in the right spot here. So let's go back to my original, back. Okay, so do this black, sorry. Okay, so what about the maximum, the minimal degree, not the maximum, the minimal degree is 3 here. So this tells me that, why is this thicker than normal? Oh, I guess this is what I want, okay. Okay, sorry, let's again look at, is there a cut vertex? What do you think? Yes, there is one, because if I remove this guy and everything that connects with this guy, all the edges that are coming out of that guy, I get two separate disconnected graphs. So there is a cut vertex, so C is a cut vertex, and therefore this graph has vertex connectivity 1. In other words, C is really a weak spot here, because if it falls, the network fails. Okay, let's think about the edge connectivity. I don't see any single edge that would disconnect this whole thing. Okay, so I hope that is clear. Let's start looking for 2. So there, in other words, there is no cut edge, but is it possible to disconnect with 2? Well, let's try a couple of possibilities. It's again, there's a certain symmetry, though it's not fully symmetrical, right? Because this vertex 6, there's only one vertex with degree 6, so it was a weak spot. So you might think I'm going to try to get some edges away from it so that it disconnects. But you see, even if I remove 1 or 2, the whole thing is still connected. Or I could try instead of remove one of those, but you see it doesn't really disconnect anything, right, if I do this. Okay, so perhaps I should not look for there. Let's look at a weak spot where the degree is very small. Perhaps by removing some edges, the whole thing gets disconnected here. But again, I don't see, for instance, if I remove this one, there's nothing I can remove next to make it disconnected. I can remove that one. Oh, no, of course, that's not really, if I remove this one, it's only this one that will go. Okay, so again, I don't see how removing 2 gets the thing disconnected. As I said, it's rather symmetrical. What happens at E is rather same what happens as A, B, D, and H, so I don't expect anything else there. D is again slightly different, but again, it's actually more connected to the rest, so even you see here 2 removing doesn't disconnect it. What about this central guy? If I remove that one, okay, but then I still, even with 2, I cannot get anywhere. So it seems there are not even 2. There's no edge cut that remove 2 of size 2. So what's the next best is size 3, and now here we see one, right? Because actually I was about to do it. 1, 2, and 3. Sorry, again, this 2 steps, right? 1. This thing is a little bit. You see here 3. So let's list this then. For we have an edge. So this was 1, right? So we have an edge cut. Is the edges, which edges? The edge CD, the edge CG, and the edge CF. If I remove these 3, then the graph this gets disconnected. Now, it's not the only 3, because we know that 3 is the maximum number, right? And we know that if you have a vertex of degree 3, you can remove the 3 edges around it to disconnect it. So in either case, this is a bit different, but anyway, we still see that lambda of G is 3. So in this sense, this although this is weak as far as the routers is concerned, the network, the computers is concerned, it is rather strong as far as the fiber connections, the edges is concerned. Okay, the next one. Yeah. So let me draw this lambda, but I'm not gonna. Just gonna do them here. Again, the degrees 3, 3, 1, 2, 3, 3, 3, 3, 3, 3, 3, 3, 3. It's a kind of uniform graph. These are actually special graphs. We often are interested in graphs like that. They all have degree 3. So the maximum degree here, the minimum degree, which is also the maximum degree, is 3 here. So we know that these values, kappa and lambda, can either, it will be 1, 2, or 3. Okay. Is there a cut edge, a cut vertex? I don't think so. As far as you can see, whatever vertex, and this is again rather symmetric, right? So either we can remove one of these top vertices, but that does disconnect the rest of the part. Of course, we should not look at A anymore, A is gone, right? But I can remove one of the central ones. Again, it doesn't disconnect anything. And I can one of the outer ones, but also that doesn't do anything. And symmetry tells me that is the only situation. So in this case, our conclusion is there is no vertex, cut vertex. So we know that the value is at least 2. So now is the question, is it more than 2? So are there 2 vertices that I can remove to make the whole thing disconnected? Okay, let's. In the meantime, I'm also thinking of. So we know this is at least so the 2 possible. So 1, 2, or 3, and this is 1, 2, or 3. Or these are the possibilities. I've now ruled out 1. This also rules out 1 here, by the way, because of the inequalities, right? This has to be at least this much. So if I've ruled out 1 here, I ruled it out there too. Okay. I see something. While I kind of don't see immediately perhaps what to do here, I see a bit better what the... I know there is no cut edge. Because there's no cut vertex, there can be no cut edge, if you think about it. And also because of the inequality. But I see there's an edge cut of 2 edges. There are 2 edges that if they break, if they fail, then the thing gets disconnected. And I hope this is clear, right? It's the top and the bottom one. So I see here that there is let's call this, there's a cut edge. This is the set consisting of AB and KL. So this tells me that the lambda of this graph, the edge connectivity of this graph is 2. But this also therefore tells me, from this I can deduce that this must be 2. I haven't found them, but I know that must be 2. So now I can start looking for them. Actually, let's see. If I remove this one, okay, I now see. If I remove this one, okay, so these 2 do disconnected. Okay, so sometimes you have to kind of think about which is the first one that I can see what is happening. Okay, next, the last graph. Again, the degrees are 1, 2, 3, 4. I think they're all 4 again. This is one of the. No, that's not true. 1, 2, 3, 4. This 2, this kind of. Oh no, that's because I forgot to draw one. This is missing. So let me do this. Yeah. They're all. This is also one that has degree 4 everywhere. So here now, we know that the possibilities are 1, 2, 3, 4, 1, 2, 3, 4. Unfortunately, it's quite a lot of possibilities. It's rather quick to see that no edge remove is... no vertex, removing a single vertex will never disconnect this. There are way too many connections here. So we can rule this out, and if this is ruled out, there's also this ruled out. So no cut vertex. There's no cut vertex. So what about what to do now? Okay, let's see whether we can do 2. Right? Now again, this is rather symmetric, and we have basically 3 outer and 3 inner ones. So let's try to do what happens when I remove one of the outer ones. Oh, that didn't work properly because I didn't draw my lines fully. See, it has to kind of, I have to touch everything with my eraser to get it. No, it's not going to work. Wait, let me do this again then. See, so there's this one, and then there is this one, and then I still have to make the. Okay, let's hope that it works this time. Yes. So doesn't disconnect it. So oh yeah, one, but we know one doesn't never do it. So but this is still rather quite disconnected, right? There's no single vertex that will disconnect anything. So we see already that it definitely there is no vertex cut that contains A. Okay, let's go back. Now, therefore, D and F are the same. So let's look at inner ones. What happens if I remove one of the inner ones? And again, this is not going to work properly, so I'll do it in 2 steps. I hope you saw that I didn't cheat here, right? Okay. Still quite connected. Is there anything I can remove here? I could try to remove this guy, but that doesn't work. Or I could remove the inner guy. That doesn't work. I could try to remove this guy, which also, by the way, removes this thing, but it still is connected. So, and then, well, A we know is not going to be part of it already, so with this one, which also removes this one, by the way, but it still not disconnects. So what is this a conclusion here? There is no, we see that 2 has to be ruled out as well. Sorry, this is a bit too thick, right? Okay, so also 2 is ruled out. That means it's also ruled out here. So now we have either 3 or 4. Okay. Okay, let's see what happens here with 3. Can we do 3? Okay. Or perhaps we could now start thinking. See, the bigger the numbers are, perhaps now I want to rule out 4. If I can, I want to rule out 4. Or I will have to rule out 3, one of the 2. If I rule out 4, perhaps I can already rule it out on the edge side because that's a bigger number. So is it possible to remove 3 edges to disconnect this? But even that I don't think is possible, right? Even if I connect this one, okay, there's 1. All right, I could do this one. It keeps being very connected, right? And let's see if I just randomly choose, even that doesn't seem to work. This was edges, right? So I was now trying to see whether perhaps I could find. Sorry. I was seeing whether I could find perhaps 3 edges that I could remove. Doesn't seem to be. So let's go back to our vertices and see whether we can remove them. So if I remove 1, I remove another one. And I remove this one, it still seems to be connected, right? It still doesn't break down. And, well, we know, well, yeah, okay. So that's trying to do A. Okay, what else could I do? Well, okay, what about if removing the middle one, because that's the one that's most connected? I still have this cycle that if I remove one more, it's still going to be connected, so I cannot find 3, it seems. This was, I don't know, which one did I remove? This one? Oh yeah, that was that one. So trying to do it with an outer one doesn't seem to work. What about if one of the inner ones? Okay, what can I now do? I now have everything still has a lot of degrees still, so I don't really see what I can do here to get disconnected. This one? No, there's nothing I can do now. We have only one more option, right? This one still keeps being connected. So here it seems like even 3 is not possible. So 2 is already ruled out here, therefore 3 is now also ruled out. And that case tells me that kappa of G is 4, and therefore lambda of G must be 4, because it has to be at least that much. Okay. All right, so let's go to the next problem. I don't want to be too long, spending too much time on this. This is a very nice puzzle about, we have, what is it here? We have a farmer, F, that's a farmer. It's an old puzzle, and I want to show you that many of these puzzles, we'll see several puzzles, can be solved using graphs. And actually they're not easy, these puzzles. So graphs is actually one of the ways to approach these things. So this is a farmer, and we have also a goat, G, a goat. for some reason he has a wolf. I don't know why a farmer wants to carry around a wolf, but he does. And cabbage. Okay. But of course, when the farmer is around, these guys behave. The cabbage is always going to behave, of course. But if the farmer is not here, the wolf will eat the goat. And in turn, if the farmer is not there, the goat will eat the cabbage. Okay, so what's the situation? There's a river here, and all four of them are on this side, and they have to get across the side, and we have this little boat that they can use, and it has the farmer in there, and one more item. And one of these items. Perhaps it doesn't have to. It can also go empty, by the way. So don't forget that. So and what he needs to do is at any time he has to avoid that any two things he has to avoid: that the goat and the wolf are left alone, and that the goat and the cabbage are left alone. Okay, so basically his goat, he has to keep a good close eye on his goat here, because it's either gonna eat something or get eaten. Okay. And for some reason the wolf doesn't eat the farmer. That would make it much harder. I don't think that's the solution then. Okay, so so what he suggests is we do the following. Any state can be consist of at any situation, any crossing. After any crossing, there's a couple of things on the left hand side and a couple of things on the right hand side. So we can represent this by a pair. So a pair, what we have is pair of things. So we will have some objects here and some objects there. These will be on the left river bank, and this will be on the right. Okay. So for instance, we could have the farmer and the goat here, and the wolf and the cabbage on this side. But we have to exclude anything. So remember, two configurations to watch for are the goat-wolf combination and the goat-cabbage combination. We never want them to be without a farmer. So these are kind of special, and therefore we will not allow them as a valid position. So the question is now, what are the possible valid conditions? Okay, let's think a little bit about this. First of all, we have the original condition where we have FGWC, FWGC. I don't know. It doesn't matter in which. Okay, I'm gonna try to a little bit, because I have to see that there are no duplicates here, and so I'll follow the suggestion of the book to do this alphabetically, at least as far as the three companions of the farmer are concerned. So all four on this side, that means this is an empty set on the right hand side. Okay, and this is what we want, is to get to this situation where everybody is on the other side. So what we're looking for is we will build the graph. So let's, for instance, see. One thing we can do is, let's say that the farmer takes his goat. Sorry, the farmer takes his goat, I'm putting it wrong, and crosses. So after he does that, what happens then? The farmer and the goat are here, and the wolf and the cabbage are there. So this is it's a possibility for a crossing, and it's an acceptable combination, because we don't have any of these dangerous situations. Okay. And moreover, there is, so this is one of the points of the graph, one of the vertices. The vertices are represented by pairs, okay? And there is a connection because there is a valid way of going from one to the other by a crossing, by a single crossing. So what we're going to do is now list all possibilities and see all possible transitions that can be done by this ferrying across the river. And what we look for is a path from here to there. That solves the puzzle. That will tell us at each time, so what has to be transferred and how to go. Now, here's another example. You might not immediately think of this. Is what can he do in this situation? Suppose we have done this one. Just to give a couple of examples of things that can be done, he can return without anything else. So he can return on his own. So if we get to this situation, and as I said, this is gone by a single crossing. Okay. The goat cannot go. The farmer cannot stay on the right hand side, and from this way we cannot bring the goat there and the farmer there. Now, what about this configuration? Is this? No. I'm sorry, guys. I'm gonna sneeze a little bit. I always sneeze in pairs. Okay, so this is also a possibility, and it's a valid state. Is it? No, it isn't, because well, it's invalid because we have. Well, actually, everybody's going to eat everything, right? So it's not a good situation, but it is possible, right? Because the farmer could just go on his own and leave everybody else. But this is not allowed. So I'll write it here, show you this is not allowed, because it has it. The wolf would eat the goat, and the goat would eat the cabbage. Well, if the wolf doesn't eat the goat first, of course. Okay, so this one is not allowed. So we're gonna not put it in there. What else can we have? Well, this was just one possibility. So I'm gonna have to make these things now a little bit smaller, right? So I'm gonna for purposes of making this legible, I'm gonna do one thing. Well, so we have I said it's a pair, but it's enough to say what is on the left side, because whatever is not on the left hand side must be on the right hand side. Okay, we're assuming he is not drowning anything in the water. Okay, so I'm gonna start redrawing this again, and we have this FWGC, and that means on the left hand side that's what we have, and our goal is to get to the empty set, and then everything else is on the right hand side. So we've seen that from WC, that's a valid combination. I can go there. What else can I do? Well, he could instead of taking the goat, let's see, what else can he take? Let's try to find all the things that he can do from this position, from the starting position. He can take the goat with him. What about taking the wolf? He cannot do that, because then he leaves the goat with the cabbage. What about taking the cabbage? I cannot do that, because then the wolf and the goat are together. So actually, from his starting position, he can only do one thing. But now we have seen one thing he can do is he can return. Okay, so that is definitely a position he can get to. He could return with both himself and the goat, but of course that would be back to the original position, so that doesn't bring anything new. Okay, is there anything else he can do when this situation? No, he's on the right hand side and he has to come back before anything else happens. So these are really the only two things he can do. Now, again, he has two options. Let's see what he can do. He can take the cabbage with him. Okay, so let's see what that happens. If it brings the cabbage with him, then the wolf would be alone here, which is fine, because on the other side he will be there. So remember, he will be at the other side. So that is fine. So although the goat and cabbage are together, he will be on the side. So this is allowed, and he can go there. What if he leaves the cabbage alone? Well, that's possible too, because the cabbage will be alone, and he and the wolf go the other side. And that's fine, because on the other side, as long as he's there, we don't have to worry about these two dangerous situations, right? Okay, so this would be the cabbage, right? Good. Now, if the wolf is on the only thing left on one side, what can he do? Well, he can return empty-handed. So the next position that he could go to is he would return to the wolf. But what would that mean is that the second side would have a goat and cabbage. He cannot leave them alone. So that's not a valid position here. So that's not something he can do. So he cannot return alone. If he cannot return alone, he has to take something with him. Now, he can take the cabbage. Remember, it's a bit misleading perhaps. the wolf is on the other side, so he has with him at this point. So let's see what is. I'll put in orange here what is on the other side, right? So that is the farmer, the goat, and the cabbage is on the other side, and so he cannot turn on his own because then he leaves the goat with the cabbage. So either has to take the cabbage back or the goat back. Okay. Now, to take the cabbage back would return him to this situation. So the only new thing he can do is take the goat back. So that's sorry. He can take the goat back. So then, what is the result then? The wolf and the goat would be there, and the cabbage is now on the other side. So you might say, oh, but why didn't he then just do this before? He could just have taken the cabbage with him and bring it to the other side. But remember, then he would leave the wolf with the goat. But this way he can do this without. Okay. When the other situation, we should look at also what happens here, right? Here we have the cabbage. So what is on the other side? The wolf and the goat. Again, he cannot go back alone because then he leaves the wolf with the goat. That cannot be. So he cannot go back alone. So he has to take something back. If he takes the wolf back, he's back to this situation. So the only other thing he can do is bring the goat back. So this is this. Keep writing it alphabetically. Okay. So this is one other option he has. Okay. Let's start from this option. What is now? What can he do? Well, he's gonna. Of course, he can also go empty-handed. He can just now cross, but he cannot do that. If he just crosses empty-handed, then he leaves the goats with the cabbage. So he can now do two things. And let's think about what would be the best thing to do is to take the cabbage with him. Let's do that. So if he takes the cabbage with him, that means the goat remains on this side, and then the wolf, the cabbage, and he will be on that side. And I hope you see that we're getting to a solution here. What is the other option is he, instead of leaving the goat behind, he leaves the cabbage behind. And then he will be... Oh no, but then we have that already, right? There's nothing new. Sorry, that we have that. That's the previous situation. Okay, so that's actually the only new thing he can do. What about the new thing he can do from this position? Well, if he leaves the wolf behind, we are back to this position. So the only thing he can do is leave the goat behind. Oh, so this is actually, sorry, that's the same as this guy here. The goat behind, and he can go from there to there. So that's another. Now, when the goat behind, what he has to do, what is the next thing he can do? Well, he can return himself. He can bring either the wolf with him or the cabbage with him. He can bring the wolf back, he can bring the cabbage back, or he can just return on his own. Is that okay? Yes, because then the wolf and the cabbage are on the other side. For some reason, wolves don't like cabbages. Okay, so fine. And so what's the last thing he now does when he is in this situation, other than stupid things, is going there. And so we have found a path between the starting position and the ending position. And this is what he do. And he has two choices. There are two solutions here. Right? It can either go this path, simple path, right? Of course, he can do stupid things and go up and down, doing the same thing. But we're looking for, he wants to go as quickly as possible. That's the simple path. And the other one would be this one. Now, there's other things. I mean, I there was A, B, C, and they didn't kind of all together, right? But the last question, part E, is actually interesting. It says, suppose that the farmer must pay a toll. And this is when we start talking about weighted graphs, and we will deal with this later, is when not every path has the same cost or the same weight or the same importance, whatever, depending on the situation. And so, therefore, there might be optimal better ones where you minimize certain costs or maximize a certain cost, depending again what you want to do. So here the thing is, every time that he crosses with an animal, he has to pay a toll of $1. So let's see. This is now about edges. So I'll do this in perhaps what color do I have? Blue. So each of these edges is gonna get a cost, either $0 or $1. because each edge represents a crossing, right? This crossing, he is crossing with the goat, so this will cost $1. Okay. What is happening in this crossing? He crosses on his own, so this is a $0 cost crossing. And this crossing, he takes the cabbage around, so it doesn't cost him anything. Okay, so this is 0. But in the other option that he had from this position, he is taking the wolf with him, so he has to pay $1. Okay. Then, what is happening next? What is happening here? He returns with the goat, so that costs him $1 because that's a goat that he's bringing with him. What is he doing next here? Let's just keep now working on this path. He leaves the goat behind and takes the cabbage, so that costs him nothing. Okay, and then what is happening next? He returns, so that doesn't cost him anything. And then finally, of course, he takes the goat, so that cost him 1. Let's look at what we have not talked about, these two here. From this position to that position, what is happening? He returns with the goat, so that cost him $1. And then what is happening on this position? He takes the wolf with him, right? Yes, and leave the goats behind. So he takes the wolf, so again 1. So let's now calculate the values of each of these. So what's the value on the green part? It's 1 plus 0 plus 0 plus 1 plus 1 plus 0 plus 1. So what I'm listing is, this is the part, and each time I list the cost of the edge. And this is 4. What is the other part, the orange part? 1 plus 0 plus 1 plus 1 plus 0 plus 0 plus 1. And this is therefore equal to 4. So we see it doesn't make a difference. Did I do something wrong? I thought there was a difference. Perhaps I've missed. Did I miss a part? I don't think so. Yeah, I think I did it correctly. Okay. Now I also gave you an optional problem, and I want to quickly say something about it. It's not an easy one, perhaps. I hope you had some fun with it. So we have 2 jugs, and in those jugs we can, so one of it 3 liter and one of 5, or gallon, is it gallon? 3 gallon and 5 gallon. And what we can do is, there are 3 operations valid. We can fill a gallon, but fill a jug, but filling means completely filling. We cannot fill it half or something like that. It's filling it, or nothing. We can empty it, but again, emptying is, well, okay, we can empty it, and we can transfer. Yeah, empty means emptying it completely, and we can transfer. Okay, and that's of course the interesting part. So again, our edges will be represented. Our vertices will be represented by the amount of water in either jug. And so this is the 3 liter jug is the first, and the 5 liter jug is gallon jug is. I'm gonna say liter instead of gallon, because let's say it again. The 3 gallon one is the first one. The 5 gallon one is the second thing. Okay, so what we can have, what are positions? Well, we could, here are a couple of starting positions, right? This is basically the first things you can have. You can either fill one of them, fill none of them, or fill both of them. These are all the positions you can have. And we can go from one to the other. Certain ones, for instance, we come from here to here by just emptying. So there's a connection here. We can also have a connection here. There's no direct Oh, and they want a directed path. Yes, okay, sure. Yes, of course. So I can go, right, I cannot go, it's a directed graph, right? Because I have to go from a full one where I empty the second jog. Here I do the same thing. And so what about this guy, the 3-5 guy? Well, assuming you can only do one operation at a time, there is no direct connection between these two. But there is then one that goes from here to there, that is by emptying the second jog, and this one from there to there, that's emptying the first jog. Okay, so that's a couple of things. Yeah, let me redraw this graph a little bit because it got a little bit squeezed in, right? So let's I'm gonna use a bit. So we have this guy, this guy, this guy, this guy. There are going to be many more, but oh no, that's not what I wanted. So there is what this is the 3-5 configuration. There's one going that way. That is the 0-5 configuration. This is the 0-0 configuration, and this is the 3-0 configuration. Where am I here? 3-0. So from there to there, from there to there, and from there to there. Now you will say, what else is there I can do? Well, remember, you can pour one into the other. So what can we do? From here, we could pour into this one. So in other words, actually, that is this direction. No, that's not it. Sorry. That's the main thing. What happens if I pour the 5 jog into the 3? Well, there is 2 gallons will remain in the 5 one. So there is a connection here. This is going to take forever if I keep doing this, so let me. This is a pouring where I pour the 5-gallon jug into the 3-gallon jug. Of course, not everything can go in there. I'm not allowed to spill. So I just fill it up and then I'm left with a 3-2. So this is where some other amount than just 3 and 5 can happen, and or 0 can happen. Okay, that's very important. Now, once I have 3-2, I hope you see there is a connection this way by just emptying that second jar. But that's kind of silly, right? Because we could have done that much easier. Okay, so remember what is the goal is. The goal is to see that from one of the evaluated positions is a position in which one of the jars has exactly 1 gallon in there. And that's not so obvious. Okay, let's think what else can I do with this 3-2 gun. Of course, pouring out the 2 is kind of stupid because I got something new and now I destroy it. And more interesting I can do is get rid of the extra water in jar 3. So I'm going to do it now this way again. So we get this connection here in this direction by emptying the first jar. Okay. One thing I could do, I'm going to now go somewhere a little bit towards my solution. There are many things. I'm not sure, I haven't really tried to put all possibilities up there. I have to think about it, but let's look at what as much as we need. Now, one thing we could do is, perhaps it's not smart, but we could do is transfer now the 2 liter into the 2 gallons into the first jar. That's again a pouring, right? That's by pouring. I cannot go back. Yeah, I could go back here, right, because I can go back here too, that's right. Right, so I can go either way here. I didn't always pay attention. I think that is, yes, of course, I could also go back here. I should say that because I can always fill the second jar, and here the same thing, so this goes back. What about this arrow here? Can I have also an arrow in the other direction? No, because I cannot just in an empty 5 jar put just exactly 2 gallons. That's not possible. Can I go back in here? Yes, that is just filling the first one, and this will be filling the second one. So yeah. Can I go back here? Is this arrow? What about this arrow? It's also, we can go in either direction, right? I hope that is clear because it's just adding 3, filling up the left one. Okay, so that's other things I can do. What else can I now do? Well, let's work with the one that I have here. What I can do is I can fill up the right hand one again. And of course I can empty it again if I would want to, so I can actually go back here. Okay, good. So what next? Of course, what I could do is, let's just look at a possibility. We have this node already. There is an edge that goes to 0,5 by just emptying the first jar. But it's kind of a silly thing. I'm returning to something, a previous position. So I didn't state it clearly, but we could as well say start from a full one or start from an empty one. You see, that doesn't really matter because you can go in either way. These four ones are kind of... So we can start with an empty one or we can start with a full one. Either way would work. We have done this kind of nice configuration that we have not seen, and then just emptying it brings me back to a very early one. So that's not a very interesting thing to do. So what else could I do with this? Okay. And here is a clever one. Oh, of course I could... yes, here's a clever one. What if I take the second jar and fill up the first one? What is the result of that? That's a valid thing, right? I can pour from one into the other, but only by filling it up. Now, there is already 2 in there, so it will become full, 3, but I have only transferred 1 gallon. That's interesting, right? Now we have again something interesting. And can I go back with this one? No. No way that I can go back. I cannot just carefully try to transfer 1 gallon from the left to the right. No, that's not one of the valid things to do. So what can I do with this one? Well, I can pour out the first one jar. I could also pour out the second jar, but is that a smart thing to do? No, but because that just brings you back to this very previous position. But 0,4, that's a new one that I can do. And now I'm there, because clever me, what I'm gonna do, I'm gonna take again my right jar and pour it in the second jar. 3, 1. That's again a pouring from the second into the first. And then if you really want to do it, let's pour out the left jar and make it 0. And I can actually go back here. So what means is there is a path starting from either of this position or this position that leads to a position where there's only 1 gallon left in both jars. I think that was, well, it definitely solves the problem, okay? And I'm not going to draw that path. Okay, so you see here, these graphs can help doing this. And I'm not saying you need a graph here, but it helps organizing your thought, seeing things what can be done, and you see, it's not a simple solution, right? The solution involves going all these like different steps we have to do.